summarize where we're at with building a 3D geologic model of the Paleozoic bedrock of southern Ontario. You can see there's a lot of names on here, and there's a team of people working on this, but I'll introduce you to those in the presentation. I started working on this project the day after I retired from the Ministry of Natural Resources, so this has been keeping me occupied and still enjoying doing geology. So the objective is to model formation contact data from the Ontario Petroleum Well database that the library maintains, translate those lithostratigraphic rock layers into hydrostratigraphic layers so that water can be modeled moving through this rock. The ultimate objective was hydrogeological objective, was to see how groundwater flows through these rocks. But we learn a lot about the geology in doing that. It's built using Leapfrog Hydro as a software, and this project will be done by March in 2019. Project scope, it covers all of South Central and Southwestern Ontario except for Manitoulin Island. And geologically it covers all the Paleozoic bedrock formations plus the Precambrian, plus the bedrock topography and the unconsolidated sediment sitting on top of the bedrock. 110,000 square kilometer area. There's the model team, so the people know behind the project, and for our purposes here's the library team here. Without the library and its people and its data, this model is impossible. And our modeler, the software guy, he's right here. He's in Ottawa, and we don't get to see him, but we know what he looks like because we have his picture. So building the model, this is the process. There's a lithostratigraphic chart, which I'll show you in a minute, and that's documents and names the layers of sedimentary rock. The formation contacts are extracted from the database, and those contacts have coordinates in XY space, geographic coordinates, and they have elevation values, a Z value. So that's how you're able to create a 3D model from. We have all the elements you need for 3D. That data is used to construct the model layers. The modeler, Charles, does that. Those layers are constrained with 3D vector objects, which sounds complicated, but I'll explain it to you a little later on, and which are constructed from already published maps. And then that model, each model is the geologists review it. Now myself and the other geologists on the team, we identify where we think there's issues. Those issues are resolved by the library staff, geologists at the library, and we run that revised data back into the model and do it all again. So we've done that 5 times. So what you're seeing here today is model version 5, and model version 6 should be the last one, and that won't take place until we get the modeler back on our team in July. The input data is the petroleum well database, basically, which is resident at the library and which is owned by the Ministry of Natural Resources and Forestry. The lithostratigraphic subdivisions, the chart of formations is mostly myself and Frank Brunton and Lee Fortner from MNRF. There's a new digital subcrop geology map, which is put together by the library staff and Maya Summers in particular. There's a new digital bedrock topography map compiled by the Ontario Geological Survey. We use Great Lakes bathymetry data. This is all digital data. There's a digital elevation model, which is a topography map of the surface, of the ground surface, and SRTM stands for Shuttle Radar Topography Mission, and the bedrock elevation in the lakes. So a lot of different sets of data. Without that petroleum well database at the library, we couldn't do this model. This just shows an example of a well record from the Ontario Petroleum data system. which is the Oracle Relational Database where all this data is resident. It's linked to a GIS, ArcGIS, to a GIS map. So there's geographic coordinates for all the well locations, and there's elevation data for each formation contact, and it's actively maintained by the library, so the data is being improved continuously. So the example down here shows, for an example, so folks, here's the formation names. That's the lithostratigraphic chart, or the names from the lithostratigraphic chart. I'll show you the chart shortly. And so each formation has a top in depths below the rig floor. This is true vertical depth, and this is the calculated elevation of each of the tops of each of these formations. Then each of these wells has geographic coordinates in the database, which are expressed here as latitudes and longitudes. So it has an X and a Y and a Z value. So without that you can't do 3D. So that gives you the 3D data that you need. Here's the geographic coverage of the petroleum wells. So you can see it's not uniform coverage, but we have 26,700 wells in the database. The model, there's usable data for 21,000 of those. Some areas a lot denser data than others, so the model better represents these areas than areas like this up here where wells are kilometers or tens of kilometers apart. This is a screenshot from Leapfrog, and it's a cross-sectional view showing just the wells. So we don't have none of the model is turned on, it just has the wells with the formations color-coded. So you can already see, there's the Precambrian rocks down below here in pink. And then all the colored layers up here are each of the 56 formations with a separate color lying on top of that. And every formation is represented by a layer. We didn't group any of the formations. This is a bedrock topography. So this is the topography on the surface of the bedrock after you've stripped off all of the quaternary glacial sediment sitting on top. These colors here, these are the highest portions of Ontario once you strip the drift off, and you get lower elevations. You go down here towards Lake Erie. There's valleys here and here, and there's a gorge running through here, so there's a lot of topography on that surface. Here's the lithostratigraphic chart, and this is a new chart for Southern Ontario. This has been released, so this is publicly available now. Just was released 2 or 3 months ago. And we've reoriented this is reoriented differently than the previous published sections. So here's the A, B, and C that you see represented up here. So these columns here represent what rocks occur in different geographic parts of Ontario. What we've done is go from the subsurface, where in this column it's entirely subsurface, and oriented the chart so it goes towards where these formations subcrop come to the surface. And the other important feature on here, because the purpose of this was for modeling groundwater flow, all these ziggy-zaggy lines on here are periods in time where these rocks were exposed to erosion at the surface in the geologic past. And so it's an erosional interval, so it's a non-depositional interval, and if that erosional interval, a lot of these erosional intervals, when the rocks that were exposed were carbonate rocks, they were karsted, and that created a lot of porosity and permeability that wouldn't have existed in these rocks otherwise. And then they're buried by younger rocks. And so these karst zones they're porous and permeable, and they're aquifers, they're layers of rock on the subsurface that contain water. This is a view of the new digital subcrop geology map that Maya compiled from all the previous published maps with there was some new geology done down here. She's incorporated that, and she's added some interpretations up in here to get the geology beneath Georgian Bay. So this is a brand new map, and I think this is available on the library website now, or will be. Oh, okay. Now here's where I talk about 3D vector objects. So if you go back to this, there's the bedrock topography. So that's 3 dimensions. There's the bedrock layers where they come to the surface. So each of these layers of rock, to make this 3D, this is a 2D map, to make this 3D, it's draped onto the bedrock topography. So that gives you a Z value now. So that is a 3D vector object. So in this figure, the 3D, this is the bedrock geology, the names of the formations draped on the bedrock topography. And so this is a 3D vector object. I've keyed out the Queenston Formation here. So on this slide down below, we've added the modeled Queenston Formation from the borehole data. So 21,000 data points with the 3D and geographic position of where the boreholes intersected the Queenston. So that's a model of the formation. And when you build the model, you truncate this layer. If you didn't have this layer to constrain where this formation goes, it would extend out past where it actually subcrops at the surface. So this constrains where this layer goes. There's a Great Lakes bathymetry. So this controls the 3D aspect of where those formations occur beneath the Great Lakes. This is a digital elevation model, which is the topography of the existing surface, with the glacial sediments still left on top. And this is a digital map from the Shuttle Radar Topography mission. So some of the challenges, I'm just showing you some of the issues that are still in this model. These little tongues, in this case the Goat Island Formation, that appear to be drooping down the face of the escarpment. This is the Niagara Escarpment I'm showing here. And those aren't real. It's an algorithm, so it can only model according to the inputs it has. And so it's things like this, the model, the modeler is going to have to take each one of these out by hand. He has to intervene in the model and remove them. So he still has quite a bit of work to do for this kind of detail. This is an example of what happens when you don't have any data. This software turns out to be a terrible extrapolator. If you don't have any data and you're looking in front of where you have data, it doesn't do very well at doing that. So this example here, this is onshore and this is Lake Huron. So we have lots of wells in the onshore area, no wells out here in Lake Huron. So the example I'm showing here is the B salt. So the model, the algorithm, has taken the B salt and it's pinched it out. It makes it thinner as it goes west, when the opposite is the case. So we have to insert some more data values. We're going to get data values from Michigan and add those to our data set in order to get these formations to continue across the lake onto the other side. This slide is showing for other errors and individual anomalies how much work was put into fixing those by library staff. So if you add these up, there's 4,000 or 5,000 manual corrections have been made by library staff to get the model to behave correctly and correctly model the geology. So this is part of that iterative process and why why the first model wasn't acceptable, or the second or the third, and we're on the fifth now. Because as we find the errors, we correct them in the database and run it again. So this whole process we don't just end up with a model, we ended up with a vastly improved quality of data in the database for anybody else who's coming along to use the data subsequently. So the next few slides are from the model as it exists now. So this is showing the 3D geology with the glacial sediment sitting on top of the bedrock. So you can see the moraine systems on here. Now I don't know if you can see the detail down in here. So with the model, there's a free software viewer. So all the images I'm showing you are using the free software viewer. You don't have to rent the software it's expensive, but you rent it by the day or by the month. And I created all these images using that free viewer. So when the model is released, you will be able to use it yourself. You just won't be able to change anything in it. So here I've turned off the drift, so now you're seeing the bedrock formations, their subcrop edges draped on the bedrock topography. So what could you do with it? You can view the bedrock topography. You can see where the mineral and hydrocarbon resources are. You can use it for scientific investigation. Of course, the simplest and the most fun thing to do is just geologic visualization. You can see all these things in 3D. You do cross sections and you can actually check the data on each well. There's modeled formation layers by geologic age. I've just put different versions on here where some of the stripping off different ages of rock. So you can turn off formations one at a time or in groups. There's the Niagara Escarpment. So you can see the Niagara Escarpment on here and any valleys eroded into it. And all these along here. You can see where the salt resources are. This is the B salt in the Upper Silurian salina group. There's the Pinnacle Reefs. The Pinnacle Reefs show up. On the first version of this, Pinnacle Reefs didn't show up at all. It was flat. They were invisible. So we knew they had some work to do. So until the Pinnacle Reefs showed up, I wasn't happy. I don't think they showed up till version 3. You can slice the model any place you want on any direction. And on any angle. And there's a different angle doing a cross section. So you can see regional structures like the Chatham Sag or the Algonquin Arch and the basins on either side of it. Can you do a cross section, turn some of the layers off so you can see I've chosen to show you the reef structures in here, the Guelph Lockport pinnacles. You can actually, we've drawn in the Kimball-Collinville fault in here, as you can see the fault displacement right here. The layers are displaced here. We've drawn that into the figure. Salt dissolution and collapse. Here's the B salt down here. You can see where the salt has been dissolved away and what's happened to the rocks up above. They either collapsed down into those dissolution features, or if this was an early feature, the rocks thicken into it because they're filling a depression that existed on the seafloor at the time those rocks were being deposited. So it gives you an idea of the timing of that salt dissolution. And you can look at individual wells. So I've turned off all the geology on here except in the well bores themselves. So each of these columns is a well bore. And this example is here. If you want to see what that particular interval is, it'll come up on the side here and give you all the relevant information for that interval in that well. So phase 2 will be to translate the rock stratigraphic model into a hydrostratigraphic model. So where's the water occur in these rocks? So this is a hydrostratigraphic chart. So this is new. This hasn't been released yet. So it's the same as the rock stratigraphic chart. The rocks that have water in them are colored on here according to the color code up here. But I'll tell you, the blue is fresh water, yellow is sulfur water, and the orange are brines, or is salt water. And you notice the fresh waters all occur close to the surface, and as you're going down into deeper rocks, you go through a transition zone of salty sulfur water, and you get into really deep rocks, you get into salt, really, really saline waters. So the next step will be after we're finished with the rock 3D model, there will be a model showing where the water occurs in these rocks. And then the numeric modelers are going to make water flow through these rocks. That's a project. They just started working on that. It's just a cross-section giving you a different view of where the water occurs in the rocks. So that sort of thing will be modeled in 3D now instead of this 2D image. And the really shallow water, that work's being done, the details being done by the Ontario Geological Survey. So this is just an example of some work by Frank Brunton. And this is a figure Frank's modified from a previous publication showing how water flows through the fractured rocks close to the edge of the Niagara Escarpment. So that sort of knowledge will be incorporated into the eventual hydrostratigraphic version of the 3D model. So in the last version of the model, if I get enough time from the modeler, we're going to add the oil and gas reservoirs. So you better strip off these formations and see where the oil and gas occurs in the subsurface and with their reservoir edges. We'll add a 3D representation of the fault locations. There's still a few remaining anomalies to fix. And we're going to incorporate, we still don't have, the Ontario Geological Survey is working on a new bedrock topography map, and we still don't have that, so that will be incorporated as well. So we're still waiting for those things. That's just a list that you can't read of. We publish progress reports as we go. And that's just a summary of where we're at. At the workshop, well, you'll be able to go, so those of you that choose to, can go and visit myself and Liz over in the corner, and you can view the model in any way you choose to. Ask us what we can do, and we'll see if we're able to do it. And over here, Maya's going to talk about, she's got some cores from the formations that I know some of that you've seen in the model here. So you can see the actual rocks that we're representing in the model, because without the data from the cores and the cuttings and the geophysical logs from the library, we can't do a model like this. So that's the real data, and this is a model that represents that data.